Alright, so this is ECNG1016. I am Dr. Amsamuj. Okay, so ECNG1016 is a course, well, it's a maths course in which we're only going to do Laplace transforms, right? Okay, so in this course, we're going to be using course webpage. Using course webpage here for 1016, right? And the link for your course webpage is already posted on your My Learning site. Right, so on this webpage, we have a set of class notes, and the class notes is available using this link here, right? And this is what your class notes are going to look like, right? Okay. All right, your schedule is the lecture and tutorial schedule would be 5 to 7, right? Typically, I will probably use the 2 hours to lecture, right? And then uh, every couple of weeks or so, what I'll do is I'll do a tutorial, right? Okay, okay, all right. In addition to your course notes, we also have some textbooks that are available on your course webpage. Okay, the one that we would use the most would be Finan, right? Because what I will do is I'll assign problems from Finan, right? And a PDF for Finan is available here, right? There's also some additional text that you can take a look at, right? But the main ones that we'd use is, of course, the course notes and this Finan here. Okay, so your assessment for the course would be two coursework exams, right? One probably in the middle of the semester and one near the end of the semester. And both of those would be worth 50% each, right? That also give you some assignment problems, right? But those are mainly for practice, right? Your assessment towards your final grade, right, really just comes from these two coursework exams at 50% each. So what you want to notice is that on this web page we have some past papers with the solutions and then also some past midterms, right? So these are not bad. These will give you an idea of what the content of the course is going to be, right? But given that the assessment is online, right? Your online the questions in these online coursework exams won't match exactly your past midterms and the past papers, right? But these won't hurt for practice, right? And then I have some practice problems already listed here, right? And as you can see, the practice problems are referring to Finan, right? Which is what I talked about earlier, right? This course reference number 3 here. Okay, so this is my contact information. The best way to get in contact with me would be via email, right? So you can use this email address here, right? So as I mentioned, this course is about Laplace transforms, right? And where we're going to use where Laplace transforms are used, right? Well, you all are electrical students. You use Laplace transforms in controls, right? So if, for example, you take a look at this web page here for this MIT course, right, on controls, right? You want to notice that the lectures here, what they start doing is they start doing differential equations. Okay, and then they get into Laplace transforms and they use Laplace transforms to solve the differential equations, right? Okay, and that is in fact our main application of Laplace transforms in this class, right? We're going to use Laplace transforms to solve differential equations, right? And Laplace transforms is a certain sort of language that you'd use in controls, right? So, for example, like certain things like transfer functions, and so, right, actually expressed using Laplace transforms, right? Okay, and transfer functions is also something that we will look at in this course, right? Okay, so in addition to controls, you'd also, as electrical students, you'd also need to know Laplace transforms for, say, your communications courses, right? And then also your Laplace transform, the methods that you learn in Laplace transform, right, would be helpful when you get into Fourier transforms, which you would use more specifically in communications, right? Okay, so Laplace transforms are particularly important for electrical students, right? And that's why it's actually done in year one. Okay. Okay, so these are main course topics here, right? Okay, you could take a look at the course notes and well, read what these main topics are, right? But what I'm gonna do right now is I'm just really gonna start with the course, right? So first thing we're going to look at is your definition of your Laplace transform, right? Okay, so what your Laplace transform is doing for you, right, is given a function y of t, right? So this t over here, the small t, is usually you want to regard it as time variable, right? Okay, so you have a function in time variable, right? Right, so we have a function in time variables such as this one over here. So this is an example of a y of t, the graph of a y of t, right? This particular function is 0 from time t is equal to 0 to time t is equal to 1. It is linear from time t is equal to 1 to time t is equal to 2. And then after time t is equal to 2, it's equal to 0, right? Okay, so this is a function of t, right? And the idea of Laplace transform is given a function y of t such as this, right? What you want to do is you want to get the Laplace transform of it, right? So given a y of t, which is a function of t, when you apply Laplace transform, what you're going to get is you're going to get a function of s, right? Okay, so this particular function, it is probably a slightly complicated because this is piecewise defined, right? You have, say, the function behaves differently on different intervals, right? On different pieces, right? Okay, so we will eventually get to something like this. This isn't really a big deal, but to start off with, what we will do is we will consider functions y of t that are simpler, right? So more standard functions such as y of t is equal to just say t, or y of t is equal to e to the 2t. Y of t is equal to cosine of 5t, right? Okay, so as I said, what you have is you have a function y of t, and when you take Laplace transform of it, you're going to get a function of s, right? Okay, right. So for example, this function, which is y of t is equal to t, right? Y is equal to t, right? The Laplace transform of it turns out to be 1 on s squared, right? Now this isn't really standard notation here, right? This is the more standard notation that we will use for Laplace of a function of t, right? But this here is really just to give you an indication of that you're starting from something in time variable t, and when you take Laplace transform, you're going to end up with something in s variable here, right? Okay, so Laplace transform of t is 1 on s squared, right? Laplace transform of your exponential here, then this is e to the 2t, right? Laplace transform of this exponential is 1 on s minus 2, right? And then Laplace transform of cosine of 5t is s on s squared plus 5 squared, right? Okay, so I mean, right away, what you could probably notice is that your Laplace transforms, right, which would be your functions of s over here, are usually going to be fractions, right? Okay, and it's fractions where you have a polynomial on top and you have a polynomial below, right? So for example, the polynomial below in the denominator here is s squared plus 5, and the polynomial on top over here is s, right? Okay, and usually with these fractions or rational functions, right, the degree of the polynomial on top is usually lower than the degree of the polynomial below, right? So this is s to the power 1, and this is s squared, so this is s to the higher power. Higher power is 2 here, right? Okay, and likewise over here, you see in 1 on s squared, the degree of the polynomial on top here is 0, right? And the degree of the polynomial over here is 2, right? Okay, so your Laplace transform, first thing, as I say, you could probably notice that once you have a function of t and you take its Laplace transform, right, what you're going to end up with is a fraction like this, where you're going to have a polynomial on top and a polynomial and s on top and a polynomial and s below, right? In this particular case, the polynomial is really just a constant, and in this case over here, the polynomial is s squared. Okay, so typically, if you typically, but not always, right? When you want to get a Laplace transform, right? You're going to use a table, right? Okay, so for example, to get Laplace transform of t, right? You're going to use your table over here, and you're using formula for t to the n, right? Notice this formula for t to the n. This is a formula that holds for n is equal to 0, 1, 2, 3, so on, right? Okay, so if you want to get Laplace of t, right, you can put n is equal to 1 into this, and you'd get 1 factorial, which is 1, and then s 1 plus 1, which is s to the power 2, which is this s squared over here, right? Okay, so that's most times you're really just going to use a table to get your Laplace transforms, right? But of course, these formula that in your table over here, right, in fact come from using a definition of Laplace transform, right? And this definition of Laplace transform you will need to know, right? Because as we saw a little earlier, right, here I have this function y of t over here. Now this function y of t isn't really like a standard function, say like a t to the n or exponential or cosine, right? This is a piecewise defined function, right? And if you have a piecewise defined function, to get the Laplace transform of it is really not going to come straight from a table, right? So that is one reason why you need to know your definition of your Laplace transform, which is this over here, right? And then of course, this is just say standard material in the course, right? So you're expected to know this definition and to use this definition here, right? Okay, right, so your definition here of Laplace transform of y of t, how you're going to get Laplace transform of y of t, right, is you're going to take your y of t here, you multiply it by exponential e to the minus st, right? So this s over here is the same s that you see in your Laplace transform. Okay, so y of t, right? So you want to get Laplace of y of t, right? You get Laplace transform of y of t, right? So you take your y of t over here, you multiply it by this exponential e to the minus st, and then you're going to integrate this exponential between 0 and infinity, right? So integrating with respect to t, right? When you integrate with respect to t, right, you have this s over here, and really you just treat the s as a constant, right? So the s is as if it was 5 or 10 or something like that, right? So when you're doing your integral here, you're integrating with respect to t, and you're integrating, your limits of integration would be 0 to infinity here, right? Okay, so probably a couple issues here, right? First of all, I'm integrating with respect to t, but I have two variables inside here, s and t, right? But as I just said, right, the s here, you're just going to treat it as a constant, right? So really you're just integrating the t, and the s is just coming along for the ride, okay? Okay, second issue over here is that s over here is going to be a complex variable, right? So the s is going to have real and imaginary parts, right? And this is how we typically write a complex number. This is your real part. The real part is sigma, right? And the imaginary part here is omega, right? Okay, so as the second issue, because S is complex, right? You need to understand how to integrate a function when you have a complex variable in it, right? And for us, it's not really a big deal, right? For us, we're just going to treat this S over here, your complex variable, just as if it was a real constant, right? So your normal integration rules that you would use as if S were real, right? You're going to use the same rules, integration rules, when S is complex, right? Okay, but I will give you an example of that to illustrate what I mean, right? And then the third issue over here is the fact that you integrate n from 0 to infinity, right? So what we need to do is we need to figure out how to deal with this infinity sign, right? So that's the third thing that we need to look at, right? And matter of fact, well, it's the most important aspect of this integration here, right? How do you deal with this infinity sign, right? Alright, so you want to consider how we deal with this infinity sign here in a definition of Laplace transform, right? So let's look at a slightly more general setup here, right? Okay, so integral, right? Here I'm integrating with respect to t, right? An integral, when you integrate in respect to t, and when your lower limit is finite, right? So this a over here is supposed to indicate that this is just some constant finite lower limit over here, but your top limit over here is infinity, right? So you want to notice that this definition on the right hand side here of Laplace transform, this is in fact just a particular case of this improper integral, right? So if we could handle this improper integral, we'd be able to handle dealing with this infinity sign over here, right? Okay, so I have an improper integral which is defined like this, right? This is not the only type of improper integral, but that's not that's not really relevant for us, right? Okay, so we have an improper integral where your top limit over here is infinity, right? Now, how do you deal with that, right? Well, how you deal with that is the infinity sign here, right? What you do is the infinity sign over here, you replace it by a r, right? Okay, so your integral of g of t dt from a to infinity, right? What you do is you replace the infinity by r, right? And now, if you're looking at this integral over here, right? Forget about the limit for the time being, and you just consider the integral of the g of t dt between a and r, right? This is just a normal integral, right? This is just, this is just normal integration. What you do is you just integrate this g of t in a normal way, and then what you do is you put in your values a and r here, right? It may look slightly confusing, but really you just want to think of this small a and the small r as just being, say, just constants for the time being, right? Okay, so once you do that, right? So that what that means is that really once you work this out, right, you're gonna get an expression, right? You're gonna get some function, right? And seeing that you have an r over here, when you work out this integral, you're gonna get something involving r, right? So you're gonna get some expression involving r, and then according to your definition of this improper integral, what you're going to do now is just whatever you worked out over here, you're going to take the limit of it as r goes to infinity, right? Okay, so right, so that's really your definition of improper integral. That's how you want to think about it. But the next sort of cheap way to think about this, right, is if you consider this expression over here and you take the limit as r goes to infinity, right? You could really just think of this r as just heading to infinity. So r would become infinity over here, which means that you have that infinity there, right? Okay, so that's a next way to look at it. And probably a final way to look at this is the issue of the infinity over here, right? What you do is you replace the infinity by r, and now you take an r goes to infinity in the limit, right? So the problem with the infinity over here in this upper limit, right? You really transfer it to a problem with your limits over here, right? Okay, so as I said before, this really will just work out to just be some function of r, your integral a to r of g of t dt. When you work this out, this is just going to be a function of r. And then what you will do is you're going to take the limit of this as r goes to infinity, right? Okay, right. So your improper integral, this improper integral here, right? Same thing over here. This improper integral on your left-hand side is said to converge, right? If this limit on your right-hand side, if it exists and is finite, right? Okay, and if it doesn't exist or it isn't finite, right, then your improper integral over here is set to diverge, right? So your improper integral on your left hand side is set to diverge if the limit over here on your right hand side doesn't exist or is not finite, right? Okay, so let's see some examples of this, right? Right, so let me remind you about some properties of exponentials, right? Okay, so this green graph over here, this is the graph of e to the 5x, right? Okay, so e to the 5x, right? I'm using variable x over here instead of t, but it isn't a big deal, right? Okay, so if you put in x is equal to 0, right, you're going to get e to the 0, and e to the 0 is 1, right? So that's why you have this intercept over here. Okay, and what you want to notice is that as your x increases, right, your function is increasing and increasing dramatically, right? Okay, so for a function e to the 5x like this, right? What's happening is that, for example, well, here I use e to the 5x, but here I use e to the 5t, right? Okay, no big deal, right? Okay, so this e to the 5t, as the t increases, right? In other words, as t tends to infinity, right? What happens is that the exponential function increases and heads to infinity, right? So one thing you want to note is that if you have an exponential function in this sort of form, right? And the coefficient in front of the t here is positive, right? The limit as t goes to infinity, right, is going to be equal to infinity, right? Okay, so you could state that more generally that if I have e to the at, right, where a here is bigger than 0, then the limit of this e to the at once t heads to infinity is equal to infinity, right? And this over here, this is a particular case, right? So this particular case is when the a is equal to 5, right? Okay. So now let's consider an exponential function, but now this is exponential function and it's going to be e to the minus 3t, right? The graphing over here to use a variable x, and here I'm using variable t, right? As I said, it's not really a big deal, right? It's the same function essentially, right? Okay, so here I have a function e to the minus 3x, right? And what you want to notice with this function over here is that as the x increases, right, what's going to happen is that the exponential function is actually going to head to 0, right? And that's because you have this negative over here, right? Okay, so, well, what does that mean in terms of limit, right? So if we take in the limit of this e to the minus 3t, right, as t goes to infinity, right, in other words, as t is increasing, right, what's happening to your function values is your function values are heading towards 0 over here, right? So that's where this limit over here 0 is coming from, right? Okay, and why you heading towards 0 over here is, as I said, because your coefficient over here is negative, right? And more generally, what I can state here is that if I want to take limit of an exponential function, e to the at, where your coefficient a over here is in fact now negative, right? Then the limit of that as t goes to infinity is in fact going to be equal to 0, right? And you just saw an example of this general statement here. In the case when the a is negative, when the a is equal to minus 3, right? So one more time, all right? Exponential function e to the minus 3t, when you take the limit of it as t goes to infinity, right? When limit as t goes to infinity. So as the t is increasing, right, along your t-axis, the function values are dropping and heading towards 0. Okay, so let's do a couple examples of improper integrals, right? So here I have this integral over here, and you want to notice it's of the form of the improper integral specified over here, right? I have infinity as my top limit. Yeah? Lower limit is a constant. In this case, the constant is equal to 1, right? And the function over here is e to the minus t, right? So the g of t is actually equal to e to the minus t, right? Okay, so I want to work out this improper integral, right? Now, according to my definition of how you're going to work out an improper integral, you work it out as a limit, right? So I want to work out the integral e to the minus t dt between 1 and infinity, right? So what you do is you replace the infinity over here by r, right? And then I have this integral here. And then once I work out this integral, I need to take the limit of it as r goes to infinity, right? So I'm using my definition over here to work out my improper integral, right? In order to work out this improper integral, we need to work it out as a limit, right? Okay, so once you have this set up over here as a limit, right, then what you're going to do is you're going to forget about the limit for the time being and really just work with the integration here, right? Okay, so as I said, once you work out this integral, what you're really just going to get is you're just going to end up with a function of r, right? Okay, so let's just work out the integral, right? So this is e to the minus t dt, right? Right, and let me just remind you how you integrate exponential function, right? Okay, so if you want to, and this you should know already, right? If you want to integrate e to the ax dx, right? Then this over here, the integral is just the same e to the ax. But what you do is you divide by the coefficient of the x here, which is the a, right? Okay, right, and then plus a constant, but this isn't really going to apply for us because what we're doing is we're working with definite integrals, right? Okay, and more generally, if you have e to the ax plus b, right, it's really the same sort of formula, right? You're going to maintain your exponential over here, which is the e to the ax plus b, and then you divide by the coefficient of the x, which is a, right? So you have 1 on a times your exponential here. Alright, so integrating e to the minus t dt, right? Your coefficient in front of the t is just minus 1, so you're going to divide by that minus 1. And then you put in your limits of integration, 1 and t is equal to 1 and t is equal to r, right? Okay, right, so you're treating r as if it's a constant, right? And here, when I put in t is equal to r, right, I'm going to get minus e to the minus r, which is just minus e to the minus r. And then when I put in t is equal to 1, right, it's going to be e to the minus 1. But remember, when I put in this lower limit, I'm subtracting, right? So I'm going to have minus here times this minus 1, which would give me a plus. So I'm going to end up with e to the minus 1, right? Okay, right. So your integral here, when I work out my integral of e to the minus t dt between 1 and r, right, I get e to the minus 1 minus e to the minus r, right? And I think as I mentioned a couple times, really this is now just a function of r, right? And this function of r, you're going to now take the limit of it as r goes to infinity, right? Okay, so the idea of working out the improper integral is that you replace the infinity over here by r. You do this integral here first, right? You're going to get a function of r. And then that function of r, you take the limit of it as r goes to infinity. Okay, so now working out taking the limit of this. This is a limit of a difference, so you could take the limit of the individual pieces. This over here is e to the minus 1. E to the minus 1 is just 1 on e, which is just some constant, right? Okay, so this isn't going to change with r, so the limit of this as r goes to infinity is just going to be e to the minus 1, right? And here what I have is limit of, on this, for this second limit here, I have limit e to the minus r as r goes to infinity, right? And I talked about this, right? The fact that the coefficient in front of your variable here is negative means that when you take the limit of this as r goes to infinity, you're going to get a limit being equal to 0, right? Okay, so when you work out this limit here, you're going to get e to the minus 1 minus 0, which is e to the minus 1. So your limit here, when we work it out, it actually exists, right? And it's finite, right? This is a finite number, right? So you say that this improper integral over here, it converges and in fact is equal to e to the minus 1, right? So that's what I've written over here. Your integral e to the minus t dt between 1 and infinity, it converges and is equal to this what it converges to, which is the e to the minus 1. Alright, so let's do a second example of an improper integral, right? So the one that I just did was e to the minus t, right? And now this one is in fact e to the t, right? Okay, right. So we're gonna work this out the same way, right? You use your definition of your improper integral, right? You replace the infinity over here by r. We're gonna work out this integral first, and then take the limit as r goes to infinity, right? Okay, so we work out this integral here, right? Integrate e to the t, we're just gonna get e to the t. And you put in your t values, t is equal to r and t is equal to 1, so I get e to the r minus e to the 1, right? And now I take the limit of this as r goes to infinity, right? Okay, so taking the limit of this as r goes to infinity, right? Your remember your variable over here, the coefficient in front of it is positive, right? So in this case, when you take the limit of this exponential, what you're gonna get is you're gonna get infinity here, right? Now this over here is just a constant, right? So really how you want to read this is that this e to the r is just going to get larger and larger, right? With this sort of finite offset over here, right? Okay, so this, well, or in other words, the e to the r over here, this is what's going to control or dominate the behavior for this limit here, right? Okay, so as r goes to infinity, this e to the r will head to infinity. And infinity minus a finite number is still just infinity. So what you end up with is infinity here, right, as your answer. Right? Okay, so your improper integral, it is not finite, right? Okay, so what you say is that your improper integral, it diverges, right? And it doesn't have a value, right? It diverges. So I can actually interpret this limiting process for my improper integral. I could interpret it graphically, right? Okay, so I have it's the same problem with the e to the minus t integral between 1 and infinity of e to the minus t dt, right? Okay, so so how do I work this out? I work it out using my limit definition, right? So what I need to do is I need to integrate e to the minus t dt between 1 and r, right? And that's what this picture is doing for me over here, right? I have 1 over here, right? And I got r is a value larger than it, right? Now what you're going to do is, now when you work that out, right, you want to notice that you're going to get the area under the curve is equal to this integral over here, right? Now what you want to do is you want to take this r over here and you're going to shift it along, right? And you want to see what happens, right? Okay, so we want to take this r over here and shift it along, right? So what we're going to do is you're going to increase the r here. Okay, and notice when you increase your r, right, what you get is you get a larger area, right? And the idea is that once you keep increasing the r, the area under the curve is going to get bigger, right? But it isn't getting drastically bigger, right? If you notice, it's just increasing a little bit, right? Okay, so the overall the area that you're going to get, right, when this r heads to infinity, right, is in fact bounded, right? It doesn't head to infinity. It's bounded by this finite area under your curve. As the r heads to infinity, right? Okay, so what you have over here is integral, right, of e to the minus t, and this is from 1, and in this case the r is equal to 3, right? Now as the r keeps increasing, the area will increase, right? But overall the areas that you get even when the r increases is not going to exceed e to the minus 1, right? And matter of fact, as the r heads to infinity, you're going to end up with the value e to the minus 1, right? Okay, so the reason why you have convergence in this case is as r goes to infinity, right? The area really doesn't increase that much and just gradually is going to converge to this e to the minus 1. Alright, so next issue that we need to deal with is the fact that this s over here can be complex, right? And remember we said that if s is complex, we can write it in terms of real and imaginary parts, where the real part is sigma and the imaginary part is omega, right? Okay, so just a definition here, right? An expression such as this, right? Where u of t is a real valued function, right? In other words, this expression over here doesn't have any complex numbers in it, right? The v of t over here is also real valued, right? But notice I have u of t plus jvt, right? So this j, of course, is your imaginary constant, right? Okay, so this over here, it defines a complex valued function, right? Which means that if I put values in for t, right, I'm going to get a complex value out, right? And let's see an example of that, right? Okay, so for example, this function over here, this function is complex valued, right? Notice I have this j over here, right? And it's of the form where I have this is my u of t here, and the v of t is the 4t, right? So I'm comparing to this expression, right? Okay, and if I put in a certain value for t, say for example, like t is equal to 2, right? What I'm going to get is I'm going to get a real number here. So I'll get 16 minus 1, which is 15, right? And here, if I put in t is equal to 2, I'm going to get 4 times 2, which is 8, right? But it's 8 times j. So overall, what I get is a complex number, right? Okay, so this function over here is complex valued, right? Which means that when I put in a real number, I'm going to get a complex number, right? Okay, right. So now what we want to do is we want to see, well, how do we actually integrate uh, a function that is complex valued that is of this form, right? In other words, you have your real part over here, and then you have your imaginary part separated over here, right? Okay, now how you integrate something like this, this is a definition of the integral, right? What you do is you just integrate the real part and the imaginary part separately, right? So you split this up, you pull out the j here, and then you just integrate the u to the t and you integrate the v to the t separately, right? Okay, right? Okay, so let's see an example of using this here, right? Using this definition of a definite integral of a complex valued function. Okay, so I want to integrate this here, right? Okay, and I want to use this definition that I have for integrating a function that is complex valued, right? But notice over here, this function is written in a certain form, right? You have a function u of t over here, which is real valued. You have a function v of t over here, which is real valued, and then you have this j over here, right? And this isn't exactly of this form, so what I can do is I can just expand this out, right? Okay, and if I expand this out in my normal way of the 2t plus j squared, right? I just expand it out using basic laws of complex arithmetic, right? I'm going to end up with 4t squared plus 4tj plus j squared, which is minus 1, right? And I can separate the real and imaginary parts as 4t squared minus 1 plus 4tj, right? So now that's in this form over here, right? ut plus jvt, right? Okay, so if I want to integrate this 2t plus j squared, right? How I can do it is as I did above here, right? I expand it out, right? And I'm just going to integrate the real and imaginary parts separately as specified by this definition over here, which tells me how to integrate something that is complex valued, right? Okay, so integrate the 4t squared minus 1, and when I integrate the 4t squared minus 1 between 0 and 1, this is just normal integration here, right? And I'll get 1/3, right? I notice over here, because I pull the j out, this over here is also just normal integration, right? And when I integrate the 4t between 0 and 1, I'm going to get 2 over here. So overall, my answer would be 1/3 plus 2j, right? Okay, so what I'm saying over here is in order to do my integral here, right? And this integral is complex valued, right? First way to do this is you can you expand it out, right? And you separate the real and imaginary parts, right? And then with this imaginary, and then how you integrate, right, is you integrate the real parts separately, And then how you integrate this imaginary part is you really just pull the j out, and then you would integrate the function over here, which is 4t, right? So now what you have is just two real valued integrals, right? This integral from 0 to 1, 4t squared minus 1 dt. And you have this integral over here, 4t between 0 and 1, right? So you integrate those, and then once you work it out, and then finally the last thing is you put back your j, right? Okay, so that's one way of doing integral of a complex valued function, right? But the next way, and this is the way that we're going to use when we're doing our Laplace transforms, is really if we want to integrate over here, right? You just treat this imaginary constant as just if it were a real constant, right? Okay, so if you're going to integrate this now, you're not going to use any sort of special rules or laws or anything like that. All you're going to do is just use your normal integration rules that you would have used if the j was just a real number, right? Okay, so if we're going to integrate this, right, well, how would you integrate this, right? Well, basically what you'd need to do over here is you're going to use a substitution, right? ut plus j, right? Okay, so that's one way to do it, right? But the next way to do this is really, what you're doing is really just integrating the bracket, right? So if you integrate in the bracket, you're going to get 2 plus 1 over here, which is 3, right? And then you're going to be dividing by a constant, right? And you want to make sure that the constant that you have over here is, well, when you work backward, you're going to get back 2t plus j squared, right? Now, if I have 2t plus j, and this needs to be a 3 over here because I had a 2 over here. Remember, the 2 plus 1 gave me a 3, right? Okay, when I differentiate this, right, I'm going to get a 3 coming down over here. Then this will be 2, and then when I differentiate the inside, I'll have a 2, right? So in order for me to get back this over here, right, this would need to be a 6, right? Okay, so if you want, you sort of working backward, right, to figure out that this constant here is a 6, right? If you're not happy with that, you could actually use a substitution. U is equal to 2t plus j to work this out, right? But as I said, really, this over here, this is what you're doing is integrating a power. So you're going to get 2 plus 1, which is 3 over here. And you really just want to make sure you're dividing by an appropriate constant so that when you differentiate this expression here, you're going to get back to 2t plus j squared, right? And notice this is what I would have used if the j was actually just a real number, right? So I'm using normal integration rules, right? Okay, and now once I have this, what I do is I put in t is equal to 1, and I put in the t is equal to 0, right? And when I put in t is equal to 1, I'm going to get 2 plus j cubed over here. And when I put in t is equal to 0, I'm going to get j cubed here. Notice what I did is I pulled out the 1 and 6 from before, right? And all I need to do is just work this out, right? So expand this out, you'll get 2 cubed here. You're going to get 3 times. Okay, so here, there's an error here. This should not be 2 cubed. This should be 2 squared, right? Because what you're doing is you're using binomial theorem to expand this 2 plus j cubed, right? Okay, so I have 2 cubed over here, 3 times 2 squared j, right? Plus 3 times 2 times j squared plus j cubed, and then minus this j cubed from on top here, right? Right, so your j cubed will cancel with the minus j cubed. I end up with 8, right? This is 3 times 2, which is 6, times minus 1, which is minus 6. So I end up with a 2 here. And then the 3 times, which this should be 2 squared, right? So 3 times 4 would give me 12, right? Okay, so I end up with 1/6 times 2 plus 12j, right? Which is 1/3 plus 2j, right? Okay, so I did the same problem 2 ways, right? In this case here, in order to work this out, I expanded the 2t plus j squared, right? And I got a function 4t squared minus 1, and then I got a function 4tj, right? And I integrated the 4t squared minus 1 and the 4t, right, separately, right? And then I just put the j in front of the integral with the 4t, the integral of 4t dt between 0 and 1, right? Okay, so that's doing it this way, and then this way over here, what I did is I really just used normal integration, and the j over here I just really regarded it as being real, right? And I used my normal rules that I would have used if the j were real, right? Okay, so the point I want to make over here is, while this is your formal definition of integrating a complex valued function, really for our purposes in this class, when we do an integration, and if we have a complex number in the integral for the purposes of this class, right? You really can just regard the complex number as just being real and just use your normal rules that you had from before, right? That you know from before. Okay, so this is, recall, this is a definition of a Laplace transform, right? If we want to get Laplace transform of a function y of t, what you do is you multiply the y of t by the e to the minus st, and then you integrate from 0 to infinity, right? Okay, so now we know how to deal with integral from 0 to infinity. We work it out using a definition of an improper integral, right? And we also know how to deal with this s over here being complex, right? Okay, right, so Laplace transform of y of t is defined as this integral here, right? And this Laplace transform is defined only for the values of s, where you're going to get convergence on the right hand side here, right? Okay, if you do not get convergence, right, if for some value of s you do not get convergence, then your Laplace transform is not defined for those values of s, right? Okay, so let's see an example of that, right? So we want to use this definition here to show that Laplace transform of e to the 3t is 1 on s minus 3. And this only, you're only going to get convergence, right? Laplace of e to the 3t is 1 on s minus 3 only for the values of, only for the cases when the real part of s is actually bigger than 3, right? So you want to recall that for our purposes, the s is complex, right? So s over here is complex, right? So you're going to have your Laplace transform of e to the 3t is going to exist and be equal to 1 on s minus 3 only when your real part of s, right? In other words, the sigma over here, when it's only when the sigma is in fact bigger than 3, right? Notice your convergence over here, the existence of the Laplace transform, right? It's not conditional on the omega, right? It's only conditional on this real part over here, the sigma here, right? Okay, so we use our definition of Laplace transform. Laplace of e to the 3t is e to the minus st times e to the 3t, right? Then you integrate that between 0 and infinity, right? Okay, so let's multiply these exponentials together, right? And when you multiply the exponentials, what you're going to do is you're going to add the powers. So you're going to get the power would be minus st plus 3t. And I want to rearrange that a little bit, right? So what I do is I factor out the t, right? Okay, and then I pull a minus sign out, right? So when I add these powers, minus st plus 3t, that's equal to minus s minus 3 times t, which is what I have over here, right? Okay, right, so really that's just rearranging a little bit by multiplying the exponentials and adding the powers, right? And now what you do is integrating from 0 to infinity. So this is an improper integral, right? From 0 to infinity over here, this is an improper integral. So you replace the infinity by r, and you're going to take the limit as r goes to infinity, right? Okay, so what we're going to do is we're going to split into cases. So we split in cases s is equal to 3 and s not equal to 3, right? So first let's consider the case s is equal to 3, right? Okay, so what happens when s is equal to 3, right? When s is equal to 3, I'm going to get 3 minus 3 over here, and 3 minus 3 is 0, right? Okay, so I end up with e to the 0t, which is e to the 0, and e to the 0 is equal to 1, right? So when s is equal to 3 over here, this exponential will reduce to 1, and therefore I'll be working out integral of 1 between 0 and r, right? Okay, and when I integrate 1, I'm going to get t, right? And when I put in my limits 0 and r, I end up with r, right? Okay, and then finally evaluate your limit, right? So integral over here works out to be equal to r, and then you take the limit of that as r goes to infinity. And clearly that's going to be infinity over here, right? Okay, so what that tells you is that you're not going to have convergence when s is equal to 3, right? Because your improper integral, which was this improper integral, which is equal to this, does not converge when s is equal to 3, right? So you see a case where Laplace transform of e to the 3t doesn't exist when s is equal to 3, right? Okay, so now let's consider cases when s is not equal to 3. Right? Alright, okay, so far what we have is Laplace of e to the 3t is equal to this expression, right? This is using the definition of improper integral. Okay, now we work in with s not equal to 3, right? Okay, so again, if you want to work out your improper integral, first you're going to integrate here, do this integral, and then finally evaluate the limit as r going to infinity. So for the time being, we're focusing on the integral. And to integrate your exponential over here, you divide by the coefficients of the t, right? And the coefficient of the t is minus s minus 3, right? Okay, so integrating this gives me the same exponential, and then I divide by the coefficient of the t, which is minus s minus 3. And I need to substitute my limits, which would be t is equal to 0 and t is equal to r, right? Okay, putting t is equal to 0 into this, right? Okay, let's do the t is equal to r first, right? So putting t is equal to r into this gives me e to the minus s minus 3r over here, right? On s minus 3 with a negative over here, which is this here, right? I'm putting t is equal to 0 in gives me e to the 0, right? And e to the 0 is 1, right? So I get 1 on minus s minus 3, right? But remember, with this t is equal to 0, what you're going to do is you're going to be subtracting, right? So this is your second limit over here. So it's going to be the negative of e to the 0 minus s minus 3, which means that the two negatives will cancel. And I'm going to get 1 on s minus 3, right? Okay, so I need to take the limit of this, right? Now this over here doesn't involve r, right? Okay, so if I'm taking the limit of this, you could take the limit of both expressions and taking the limit of this expression over here, 1 on s minus 3. This is independent of r, so I'm just left with this 1 on s minus 3, right? And now what I need to do is I need to take the limit of this expression, e to the minus s minus 3 on r, divided by s minus 3, right? And notice over here I can pull out the 1 on s minus 3, right? So over here, overall, what I get is 1 on s minus 3 minus 1 on s minus 3 times this limit over here, right? Now, you want to notice what my answer is, right? My answer is the saying the Laplace of e to the 3t is 1 on s minus 3, right? And notice I have Laplace of e to the 3t is equal to this expression. Here I'm seeing the 1 on s minus 3. Okay, so what that means is that under certain conditions, this limit over here will head to 0, right? And the condition where your limit over here will head to 0 is when your real part of s is bigger than 3, right? Okay, so what we need to do is we need to examine this limit over here, right? And we want to see when is this limit going to be equal to 0, right? And when it's going to diverge, right? Okay, so we're taking a more careful look at the limit of this exponential here, right? We're looking at the limit of this exponential, and what we want to show is we want to show that the limit of the exponential here is going to be equal to 0, right, when your real part of s is bigger than 3, right? And you're going to diverge when your real part of s is less than 3, right? Okay. Right, so how do we do that, right? Well, what you want to remember is that your s over here is a complex constant, right? So we're going to use the fact that S is complex, and we substitute that expression sigma plus j omega in for S over here, right? Okay, so we substitute it in, and the S is equal to sigma plus j omega, right? We could separate into real and imaginary parts, right? Okay, and here this is this sigma minus 3, right? What you could do is you could break up this sum into sigma minus 3 times r, right? Plus j omega r, right? And what you have is a sum of powers over here, which means it's a product of exponentials, right? Okay, right. Now that I have this product of exponentials, right, you want to notice here that this r over here is real and the sigma over here is real. So this is not complex over here, right? So this we can easily get the limit of this as r heads to infinity, right? Okay, and now we also have, so we have this e to the minus sigma minus 3 times r, right? And then that's times this exponential e to the minus j omega r, right? And you want to remember this exponential here, e to the minus j omega r. What we could do is we could use Euler formula to write this e to the minus j omega r as cos omega r minus j sine omega r, right? Okay, and that means, right, so now I have this exponential times cosine minus j sine, right? So I take the exponential, multiply it against the cosine, and take the exponential and multiply it against the sine, right? So let's consider this expression with the exponential times the cosine, right? Okay, so and we want to look at the graph of this exponential times the cosine for different values of the sigma, right? So in particular, we want to look at it when the sigma is bigger than 3 and when the sigma is less than 3, right? Okay, so if the sigma is bigger than 3, right? For example, if the sigma is 5, right? Then what you'd have is 5 minus 3 over here. But that would be negative of the 5 minus 3. So that's a negative exponential, right? Now, exponential of, say, like e to the minus 2r times the cosine, right? The graph of it is actually going to look like this over here, right? Okay, so it's going to, this is a damped sinusoidal, right? Okay, you have, basically, it's this cosine over here trapped in an enveloped formed by the exponential e to the minus sigma minus 3r and minus e to the minus sigma 3 minus r, right? Okay, so anyway, so it's a damped sinusoidal, and notice with this damped sinusoidal, what's going to happen is that as r tends to infinity, right, your sinusoidal is going to damp down to 0 over here, right? Okay, so what I'm saying is that this here, this exponential times cosine, the limit of this is in fact going to be 0 when the sigma is bigger than 3, right? Now, if the sigma is in fact less than 3, so for example, if the sigma is 1, right, then you'd have 1 minus 2, 1 minus 3, sorry, which is minus 2, and then minus minus 2, which would be plus 2, right? So I'd have e to the 2r cosine, right? And in that case, when I have a sigma that is bigger than 3, sorry, a sigma that is less than 3, a sigma that is less than 3, such as when the sigma is equal to 1, right, over here, sigma is equal to 1, right, what would happen is that if the sigma is equal to 1, I would have, as I said, 1 minus 3, which is minus 2, and then minus minus 2, which would be plus 2, right? So, for example, if I have e to the 2r, now it's again a sinusoidal, right? Line inside an envelope, but this is no longer it's not damped, right? What's happening is the oscillations are actually increasing in magnitude as you go along, right? And what you want to notice over here is r tends to infinity, right? This is not going to converge to 0, right? This in fact will oscillate between large and small values over here, right? So this limit over here in fact is not going to exist when the sigma is less than 3, right? Okay, so what that means is we're only really going to get convergence when the sigma is bigger than 3, right? Okay, but how can we show that formally without a graph, right? Well, what you want to realize over here is here I'm taking a limit, right? And if I'm taking a limit of a product, it's a product of the limits, assuming convergence, right? Which we will assume, right? And here I'm taking, okay, so limit of the exponential times the cosine, which would be limit of the exponential times the limit of the cosine, right? And likewise over here, I can do the same thing here, right? Okay, so here, right, this limit here is of the exponential is only going to head to 0 when the sigma here is in fact bigger than 3, right? Because when the sigma is bigger than 3, right, what you're going to have, that looks like this here, right? That's decaying down to 0, right? We talked about this, right? An exponential, when your coefficient in front of the r over here, when that's negative, right? Then that's going to head to 0, right? Okay, so this expression over here, right? Your limit here is going to be 0 when your real part of s, the sigma, is bigger than 3, right? And likewise over here, this limit over here is going to be equal to 0 when the sigma is bigger than 3, right? Okay, so I'm going to get 0 over here and 0 over here, right? And going back to what I have, right? Right? Remember this limit e to the minus s minus 3 times r is equal to this expression with the exponential and the cosines. Okay, and what I just showed, right, is this limit e to the minus s minus 3 times r is going to be equal to 0, right, when your real part of s is bigger than 3. Right? So when your real part of s, which is the sigma, is bigger than 3, these limits of exponentials are going to drop to 0, right, which means that the entire expression would head down to 0, right? Okay. Right. And then when your real part of s is less than 3, what's going to happen is, well, this is what's going to happen when your real part of s is less than 3, right? When the sigma is less than 3, your exponential in this case is just going to keep increasing, right? In which case, well, you can't argue for convergence over here. What's going to happen is this limit is not going to exist and this limit is not going to exist, right? So overall, what I get is I get that the result that I have stated over here, that your limit of the exponential is going to be equal to 0 when the sigma is bigger than 3, and it's going to diverge when the sigma is less than 3, right? Okay, so what that tells me here is that my Laplace transform of e to the 3t is going to be equal to 1 on s minus 3, right? This will drop to 0, right? Provided that the real part of s over here is bigger than 3, right? Otherwise, I'm going to have divergence, right? In which case the Laplace transform doesn't exist, right? And I have that summarized here, right? Okay, so Laplace of e to the 3t is 1 on s minus 3 minus 1 on s minus 3 times this limit. And this limit over here of e to the minus s minus 3 times r is equal to the limit with the exponential cosine and the exponential sine, right? And this limit over here is going to be 0 only when your real part of s is bigger than 3, right? Otherwise, you're going to have divergence. And therefore, what you get is Laplace of e to the 3t, right, is equal to 1 on s minus 3 minus 0, right, provided your real part of s is bigger than 3, right? Otherwise, your Laplace of e to the 3t is going to diverge when your real part of s is less than 3, and actually when your real part of s is equal to 3 also. Okay. Alright, so we have this definition, which is regions of convergence for Laplace transform, right? Right, so region of convergence for Laplace transform of y of t is the range of values of S, right? And remember S is complex, right? For which your improper integral over here converges, right? Okay, so we saw, for example, if your function y of t is this exponential function e to the 3t, right? Then your Laplace transform is going to converge only when your real part of S is bigger than 3, right? So the range of values for which you actually have convergence, right? In other words, for which your improper integral using the definition of your Laplace transform, right? So this improper integral over here for Laplace of e to the 3t is only going to converge when your real part of S is bigger than 3, right? We just saw that, right? Okay, so your region of convergence for Laplace transform of e to the 3t is real part of S bigger than 3, right? Okay, and so this is what I have stated here. Region of convergence for Laplace of e to the 3t is when your real part of S is bigger than 3, right? So remember S is complex, right? So, and we can draw this region over here in the complex plane, right? This over here is in the complex plane. This indicates this is the real axis, this is the imaginary axis, right? And real part of S bigger than 3, right? So this line over here is when the real part of this dashed line over here is when your real part of S is actually exactly equal to 3, right? Okay, so if you want, you could think of this in terms of x and y axis, right? So if this is x over here, this is corresponding to x is equal to 3, and you remember that x is equal to 3 is a vertical line like this, right? Okay, so your line real part of S equal to 3 is this vertical line, and real part of S being bigger than equal to 3 is this shaded area over here, right? And notice the region of convergence is real part of S strictly bigger than 3, right? So in fact, you don't include this vertical line here, right? So this is why you use dashes over here, right? Okay, so this here is a sketch of your region of convergence for Laplace of e to the 3t. Right, so we just saw that Laplace of e to the 3t is 1 on S minus 3, right? Provided the real part of S is bigger than 3, right? Now, the 3 wasn't doing anything in particular over here, right? So if you had, say, used a 5 over here, right? And you had Laplace of e to the 5t, what you'd get is 1 on S minus 5 when real part of S is bigger than 5, right? Okay, and what I'm saying over here is that this result over here, you can generalize this result for any real number 3 over here, right? And this is what this table entry is saying, right? So I have e to the at, right, where over here actually mean that the a is a real number, right? And Laplace of e to the at is 1 on S minus a, right? And you see in a particular case over here, if when the a is equal to 3, right, you're going to get e to the 3t. Laplace of e to the 3t is 1 on S minus 3, right? Okay, so as I said, this formula over here, right, well, what we just worked out here, Laplace of e to the 3t is 1 on S minus 3. This could be generalized into Laplace of e to the at on 1 on S minus a, right? And well, here I'm assuming that the a over here is a real number, right? But you could in fact do a little better, right? This number over here, this constant here, for example, the 3, can in fact also be complex, right? And that is what this result over here is saying, right? If I have Laplace of e to the wt, where w is a complex number, then Laplace of e to the wt is 1 on S minus w, right? Okay, and you have convergence when your real part of S is in fact bigger than the real part of W, right? In other words, when your real part of S is bigger than the A over here, right? Alright, so one consequence of this result that Laplace of e to the wt is 1 on S minus W, right, is I can replace this holds for any complex constant, right? In particular, it can hold for when w is equal to 0, right? Okay, so when w is equal to 0, I'm going to get e to the 0, right? And e to the 0 is 1, right? So what this is saying is Laplace of e to the 0 t is 1 on s minus 0, right? And e to the 0 t is 1, right? So what I have is Laplace of 1 is going to be equal to 1 on s here, right? And this is what this is saying over here, right? So what I'm doing one more time is I'm really just using this result where I'm just using that the w is equal to 0, right? When the w is equal to 0, inside this bracket I'm going to get e to the 0, which is 1. And when the w is equal to 0 on this right hand side, I'm going to get 1 on s minus 0, which is just 1 on s, right? Okay, so the result of that is that Laplace of 1 is equal to 1 on s, right? And you're going to have convergence here when your real part of s is bigger than the real part of w, right? Now, the real part of w when w is equal to 0 is just 0, right? So I end up with Laplace of 1 is equal to 1 on s when your real part of s is bigger than 0. Okay, so let's see if we can prove this result here that Laplace of t to the n is equal to n factorial on s to the n plus 1, right? Where this is result holds when your real part of s is bigger than 0, right? Okay, so you want to notice that, and okay, this formula also Laplace t to the n is equal to n factorial on s to the n plus 1, right? This holds for cases when n is equal to 0, 1, 2, 3, 4, right? So all non-negative integers. Okay, so obviously this is a general formula, so you can use it, for example, when n is equal to 1, right? And when n is equal to 1, you're going to get Laplace t to the 1 is equal to 1 factorial on s to the 1 plus 1, which is 1 on s squared, right? So you'll get this result here, right? Similarly, when n is equal to 2, you're going to get a 2 factorial, which is a 2 over here, and you're going to s 2 plus 1, which is s cubed, right? So Laplace of t squared would be 2 on s cubed, which is this result here, right? So this is a general formula, right? Once you have a parameter like this over here, right, you could consider it to be parameter n, you could consider this to be a general formula. Right, so we want to show this, right? Now, if we want to show this for each n, starting at n is equal to 0, and then n is equal to 1, 2, 3 onward, right? So how we're going to show this is we're going to show this via induction, right? And you want to remember how you do something by induction. You prove the start case, and then you prove your induction step, right? Okay, so we saw before that using this result here, right, for Laplace of exponential, if we use when the w is equal to 0, we're going to get Laplace of 1 is equal to 1 on s, right? So we know this already, right? And okay, so we want to show the start case, right? So, well, we want Laplace of t to the 0. T to the 0 is equal to 1, right? So Laplace of t to the 0 is equal to Laplace of 1, right? We know from before that we just saw that Laplace of 1 is 1 on s, right? And this 1 on s I can rewrite, for example, the 1 I can write as 1 is equal to 0 factorial, right? So I can write the 1 as 0 factorial here. And this is s to the power 1, which I can write as 0 plus 1, right? So what I have is Laplace of t to the 0 is equal to 0 factorial on s to the 0 plus 1. And that's actually of this form, right? Okay, so we just proved that this statement is equal to true, this statement is true, right, when n is equal to 0, right? Okay, this, what we see over here is Laplace of t to the 0 is equal to 0 factorial on s to the 0 plus 1, right? So what we just showed is that this statement holds in the case when n is equal to 0, right? If you put 0 in here, you'll have t to the 0, 0 factorial s to the 0 plus 1, which is what we just showed over here, right? Okay, so for the induction, we using Laplace of 1 is equal to 1 on s, which we knew from before, right? We got the start case. We proved the start case for this induction statement here, right? Okay. Okay, so now what we want to do is we want to show the induction step, right? Okay, so the form of the induction step that I'm going to use over here is I want to show this here, right? Notice what this is doing is related in the case of Laplace of t to the n minus 1 to the case of Laplace of t to the n, right? And once I have this over here, I can use this Laplace of t to the n minus 1 to get me the result for Laplace of t to the n, right? Okay, so how will I show this induction step here, right? Well, I start with my Laplace of t to the n, and this is using the definition of the Laplace transform, right? You multiplying the t to the n by this exponential here, right? This is improper integral from 0 to infinity. And now what you do is you use the definition of the improper integral. You replace the infinity by r here, right? And you take in the limit of this integral as r tends to infinity, right? So there's a mistake here. There should be infinity. And this now, with this e to the minus st t to the n, right? What you're going to do is you're going to use integration by parts, right? Okay, so you're going to use integration by parts, where you choose the v to be equal to tn and the du to be e to the minus st dt, right? Okay, and if we do that, right, you're going to have right, so you integrate this du over here, right? So you're going to get e to the minus st on minus s, right? So this here would be the u times the v, right? So the u is minus e to the minus st on s, and the v is t to the n, right? So this gives me, this is the uv over here, and then you want u dv, right? So it the u, as I said, was e to the minus st on minus s, right? And then the dv would be n t to the n minus 1 dt, right? Okay, and when you multiply the u by dv, right, what you would have is the e to the minus st on the s, right? Remember, with the integration by parts, what you're going to have is a minus sign, and the minus sign coming from the du will hit this minus to give me a plus, right? When you differentiate the v to get you n tn minus 1 dt, right? That is this n you see in the n over here, and then t to the n minus 1, right? Okay, so you have, this is using your integration by parts, right? And this by definition is Laplace of t to the n, right? And notice over here what this expression is, right? This is improper, this is using the definition of improper integral, right? Really what this is you integrate from 0 to infinity e to the minus st and then t to the n minus 1, right? So what you have over here, this is Laplace transform of t to the n minus 1, right? And so it's Laplace transform of t to the n minus 1 multiplied against n on s over here, right? What takes a little bit of work over here is that you'd need to justify that this limit over here is in fact equal to 0, right? Now how you can justify that is, this I do in my Math 2230 notes, right? Okay, so I have this limit over here, right, of minus e to the minus st t to the n on s, evaluated at 0 and r, right, which is this expression here. Right? Okay, when you put in t is equal to 0, you're just going to get 0 here. So then only thing non-zero is when you have r in it, right? So you're going to have minus e to the minus sr, r to the n on s, right? With a negative out in front, which is this expression here, right? Okay, so what I want is the limit of this as r goes to infinity, right? Okay, so, and again, you should take a look at the notes, right? But what you want to notice over here is, okay, so as r goes to infinity, right? And notice what we want to do is we consider an we want to show this when your real part of s is bigger than 0, right? Okay, so the if you consider this expression when the r is heading to infinity, right? The r to the n will go to infinity, but the e to the minus sr when your real part of s is bigger than 0, right? This actually will head towards 0 here, right? Okay, so what you have is something where the r to the n is heading towards infinity, the e to the minus sr is heading towards 0, right? And this is an example of an indeterminate form, right? You have 0 over here times infinity basically, which is indeterminate, right? Okay, so once you have an indeterminate form like this over here, how you want to do this is you want to rearrange it. So what I do is I put the exponential on the bottom, and when you put the exponential on the bottom, you're going to get e to the sr over here, right? Okay, so I have this now, and well, how would you work out something like this, right? Right, so let's see an example of working something out like this, right? When in the case the small n is equal to 2, right? Okay, so we want to take the limit of this expression when the small n is equal to 2, right? Now, as I said, right, the r squared will head to infinity as r goes to infinity. And likewise, when the real part of s is bigger than 0, the exponential over here will also go to infinity over here, right? Okay, so what because you have infinity on top and infinity below, this is still an indeterminate form, right? But once you have something of the form infinity over infinity, what you could do is use something called L'Hopital's rule, which means that you're going to differentiate the top and you're going to differentiate the bottom. You're not using quotient rule, you're just differentiating top and bottom separately. Okay, so if you differentiate the r squared, you're going to get 2r. And when you differentiate this s e to the sr, right, with respect to r, you're going to have an extra s coming out, right? So you have r squared will differentiate to 2r, and then the bottom will differentiate to s squared e to the sr, right? Now, you want to evaluate this limit again, right? But again, the same thing is happening because you have an r on top here, you have infinity on top, and then because of this e to the sr, you have infinity below, right? So this is still an indeterminate form, right? So what you need to do is differentiate it again, right? And when you differentiate again, the 2r will differentiate to 2, right? And the e to the sr, when you differentiate, extra s comes out, so you get s cubed e to the sr, right? Now this here, right, now when you consider the limit of this as r goes to infinity, right, this now is not the numerator here, the top over here is not going to go to infinity, it's constant. And what's happening here is that the bottom over here, when the real part of s is bigger than 0, right, the bottom here will head towards infinity, right, which means overall that this expression, something finite over here, something that's just getting larger on the bottom, this overall will just head to 0, right? So the idea in working out these sorts of limits here with r to the n, s, e to the sr, is you're really just going to keep differentiating, right, until you get a constant on top, and then the e to the sr on the bottom, right? And you could do this for n is equal to 2, n is equal to 3. What I have in the notes here is a general formula for any positive integer n over here, right? And this is the justification to show that the limit of this expression r to the n on s e to the sr, right? This is going to head to 0 when the real part of s is bigger than 0, right? Okay, so that explains why this limit over here is going to be equal to 0. And now what we have is Laplace of t to the n is equal to n on s times Laplace of t to the n minus 1, right? Okay, so this statement is a true statement, okay, and this would form my induction step for me, right? Okay, so if this is true for over here, the assumption that I'm making here is n here is at least equal to 1, right? Okay, so this is true in the case when n is equal to 1, n is equal to 2, n is equal to 3, and so on, right? Okay, so what that means is that it will be true for if I replace this n by n minus 1, right? Assuming that the n minus 1 is bigger than 1, right? Okay, so what I'll have over here is Laplace of t to the n minus 1 is n minus 1 on s, Laplace of t to the n minus 2, right? When I replace this n over here by n minus 1, right? Okay, so that's what I do here, right? Laplace of t to the n. This is my induction step, but now for the Laplace of t to the n minus 1, I use this 10 here to express Laplace of t to the n minus 1 in terms of Laplace of t to the n minus 2, right? And I can keep going like that, right? And when I keep going like that, what I will have on the top is n minus 1, n minus 2, right? Okay, until I come down to 2 over here on s times Laplace of t to the 1, right? And I can use the this statement over here again, right? When I have Laplace of t to the 1, right? This would give me 1 on s, right? Laplace of t to the 0, right? And Laplace of t to the 0, I know from before, is equal to 1 on s, right? Okay, so what do I have on top over here, right? What do I have on top over here is n times n minus 1 times n minus 2, right? And up to 1 here, right? So this is n factorial. And here, what I have is s times s times s n times, right? So that's s to the n, right? Okay, so what I have is n factorial on s to the n, right? But this is Laplace of t0, right? And Laplace of t0 is 1 on s, right? So what this gives me is the n factorial on s to the n plus 1, which is what I want, right? Okay, and this statement here holds only when your real part of s is bigger than 0, because you use your real part of s bigger than 0 to in fact to justify that this limit over here of the minus e to the minus st t to the n on s evaluated at 0 and r, that this limit over here is equal to 0, right? Okay, so this gives me what I want, right? That Laplace of t to the n is n factorial on s to the n plus 1 when the real part of s is bigger than 0.